Hey guys, in this video I want to discuss variance. This is the second video of a series where we try to give a rigorous foundation of probability theory for math Olympians. For defining variance, we want to consider x as a real valued random variable. So x is a random variable from the state space into the real numbers. The variance of a random variable measures how much it deviates from its mean. Therefore, we would also like the expectation of x to be well defined. In particular, we are going to assume that e of absolute value x is less than infinity. We define the variance of x as the mean squared deviation of x from its mean. So this is the expectation of x minus ex squared. We notice that the expression inside the expectation is greater than or equal to 0, and therefore it follows that the variance of x is in 0 to infinity, where this notation means the set of non-negative real numbers and infinity. It can actually happen that the variance of x is plus infinity, and I encourage you to pause the video and think about how we might construct such a random variable. A nice property of variance is that it has multiple expressions, which is why in practice we can often determine or at least bound the variance of a random variable. In particular, if we write the term inside of our expectation as x squared minus 2ex times x plus expectation of x squared, then we notice that these terms are just constant real numbers, and therefore we can apply linearity of expectation to obtain that this is equal to the expectation of x squared minus 2 expectation x times ex plus ex all squared. Finally, we obtain that the variance of x is also equal to the expectation of x squared minus expectation of x all squared. As a consequence, we have just proven that this expression is non-negative. Whenever we know the value of the variance of x, and in particular if we know that this value is small, we can use the Chebyshev inequality to prove that x must lie close to its mean with high probability. We are now going to use Markov's inequality from the last video to prove that the Chebyshev inequality holds. So let us pick lambda greater than 0 and consider the probability that the absolute value of x minus ex is greater than or equal to lambda. We can bring this expression into a form resembling our original definition of variance. Namely, this event is nothing but the event x minus ex all squared greater than or equal to lambda squared. Therefore, it follows by a direct application of Markov's inequality that our probability is less than or equal to the expectation of x minus ex all squared divided by lambda squared. Since the numerator is just the variance of x, we have proven the desired result. Sometimes we would like to bound just the probability that x minus ex is greater than or equal to lambda, so we would omit the absolute value. Since that is just a stronger condition, the same inequality is still true. However, that is not tight any longer, and I challenge you to prove that the probability that x is greater than or equal to lambda plus ex is less than or equal to the variance of x divided by lambda squared plus the variance of x, which is an improved upper bound. If you find a proof for that result, feel free to comment it below this video, since it is a little bit more tricky than the Chebyshev inequality. Now we want to use our bound from the Chebyshev inequality to prove that if x has variance 0, then x is a deterministic random variable. This might seem like a triviality. For example, if our state space were finite, this is clear. However, especially for general random variables where we need a Lebesgue integral to even define expectation, this is a really nice result. Let us suppose that we indeed have variance x equals 0. Then we want to prove that the probability that x is equal to its expectation is 1. Equivalently, we wish to prove that the probability that x is not its expectation is 0. This event can be rewritten as the union of n going from 1 to infinity of the event that x deviates from its expectation by at least 1 over n. By the union bound, this is less than or equal to the sum of n going from 1 to infinity of the probabilities of these events, which we can each bound from above by 0, since the variance of x is equal to 0, and therefore this entire sum is indeed equal to 0. For now, this is everything I wanted to talk to you about on the topic of variance. If you're still interested in learning more about variance, then you can watch the other video that we released today that is the first application of the topic. In either case, I wish you a nice rest of your day.